and welcome to the IEEE Spectrum Online presentation, Can You Meet the Demands of Evolving 5G Standards? This webinar is also part of the webinar series, The Road to 6G. I'll be moderating this presentation. My name is Dexter Johnson. And before we start our presentation, I would like to mention a few housekeeping items. For those of you using Chrome or Edge browsers, if you have Flash blocked, please click on the play button on the media player. If for any reason you have some difficulty seeing the slides or have some issues with your audio, please try to refresh your browser. This will fix just about any issue you may be having. For those of you who want to know if this session will be archived, the answer is yes, it will be archived and will be available for review within about 24 hours. And once the archived webinar is available, a notification email will be sent to all the registrants. Today in our presentation, we hope to have a Q&A session at the end. We encourage questions from the audience, so as your questions occur to you, please type them in the Q&A box provided on your computer. And you don't have to wait until the end of the presentation to begin submitting your questions. If you are looking for the PDH certificate code, this will be given in a slide at the end of the presentation. As you look over your screen, you should also see buttons that allow you to enlarge the slides. And about your volume, you may have to raise the volume on your computer as well as on the platform. At the bottom of the slide in front of you are a couple of additional widgets that may improve your viewing experience, including the green resource page with today's presentation and a link for the PDH certificate code form. Now I would like to introduce our presenter for today. Dr. Kevin Ramdas has been a leading expert in the field of telecommunications for the last 20 years and has been on the forefront in the evolution of connectivity from 2G right through to 5G. Kevin is actively involved with helping companies test and solve issues with communication products, platforms, and processes. He has also developed many courses to help professionals learn the foundations of telecommunications. He's a member of the 5G Council of Canada, TechNation, formerly the Information Technology Association of Canada, and the Institute for Performance and Learning. And with that, I'll turn it over to you, Kevin, if you'd like to begin.
Thank you, Dexter. All right. So if anybody would like to connect with me before or after the presentation, please feel free to contact me on LinkedIn, and from there we'll just get started. All right. So as Dexter had mentioned there, is that this webinar is part of a larger webinar series on the road to 6G. And in June, we had one seminar on the testing challenges of current releases. And at that point, it was release 16 from the point of view of field testing at the system level. Today, we're going to be looking at the testing challenges of the evolving 5G standard. And this presentation will be with respect to device testing. And then in November, there's another talk scheduled regarding the expectations of release 17 that will be released in Q2 or Q1, Q2 of 2022, which is next year. The aim of this talk today is for us to get a better understanding of the testing required to get a device onto a carrier's 5G network, and then the continual testing regimen that needs to happen afterwards. So in this talk, we'll talk a little bit about what testing is required for 5G devices. We're going to do a quick overview of 5G concepts and how do they pertain to testing. And then we're going to look at some of the attributes of 5G standards that lead to increasing demands on the testing systems. So, for example, we're going to be talking a little bit about some of the physical things that are happening in 5G, really talking about frequency, working with higher frequencies, and this idea of over-the-air measurements. Then we're going to be talking about about the evolution of 5G. So we're going to be looking at the yet to be defined use cases and how do you get devices ready for those as well. And also just the total bulk about the amount of testing that's necessary to get a device onto a 5G system. So let's get started here. So the testing processes that I'll cover start after the mobile device is assembled from its chipset and components. The first stage of conformance testing, we need to make sure that the device conforms to the 3GPP standard. Oops. There we go. The 3GPP is a standards organization that builds 3G, 4G, and 5G technical specifications. So if we want to build a device that works on the system, we need to adhere to those technical specifications. Beyond 3GPP, there's a testing ecosystem that includes test equipment manufacturers, like, for example, the sponsor of this talk, Anritsu, and other companies like Rohde & Schwarz and Keysight, and a number of smaller players. There's also test houses, manufacturers, operators that perform the majority of testing. And finally, there is the GCF, the Global Certification Forum, which works internationally, and the PTCRB, which works in North America, that approve all of the testing systems for 3GPP. They refine the 3GPP specs down to a set of essential test cases and practical test suites. Test equipment vendors and test houses need approval from the GCF and the PTCRB in order to create their testing environments and the overall test suites to ensure that there's a standard across the world. After a device manufacturer ensures that their device works according to 3GPP standard specifications, they need their devices to work on specific systems or carrier networks. Many carriers have a form of carrier acceptance testing. This next stage is carrier specific and focuses on the carrier's environment. The carrier might want to ensure that devices function the way that they want it to. They interoperate seamlessly within their network and provide the highest level of quality of experience to their customers. And third, there's a third set of testing called regression testing. So every single time there's a firmware update to any network element, there also needs to be testing. If there are firmware updates to the user equipment like smartphones or IoT devices, there needs to be testing to make sure that any of those changes in firmware don't affect the normal operation of the devices that are already out in the network. Already, as we look at some of the amount of testing and the stages of testing, there's quite a bit of testing that already needs to happen. And this becomes exponential when we start adding the diversity or the flexibility and options that are available in 5G and adding more diversity in network equipment. So in this diagram here, there's a lot going on. From the beginning there, we've got low frequency cells in and around that 700 megahertz range. That's the traditional frequency range that telecom carriers they're used to be working with. So 4G technologies are based off of this low frequency cell. Generally, when we're working at these lower frequencies, those are used for coverage because the propagation characteristics of low frequencies travel a little bit further and they're easier to propagate through objects and around obstacles. The issue that low frequency cells have is that there's lower throughput. There's less bandwidth, frequency bandwidth available in the lower frequencies. So the throughput on low frequencies is a little bit less. Then there are mid-frequency cells around that 3.5 gigahertz range. Generally, those are the 5G frequencies. These are the frequencies that were released just recently in North America and in Canada and the U.S. And carriers are starting to roll this frequency range out right now, so generally the frequency, in terms of coverage, this is a mid-range coverage, so maybe like that 1 kilometer range, a much smaller cell than the overall macro coverage, but it has a lot more bandwidth available at that 3.5 gigahertz range. So we can get higher bandwidths, and so in terms of what most people think of 5G as being able to provide really high speeds for your mobile device, like your smartphones, when the 3.5 gigahertz frequencies get rolled out, that's when we'll start to realize those gains in 5G technology. And finally, there's the high frequency cells up in and around that 28 gigahertz range, where now when we get up into that range, the coverage is a lot less. And we're talking about 10 meters or so, give or take. But what happens there is that the throughput is really high. There's a lot of bandwidth available at the 28 gigahertz range. So that means that we can use it for small coverage but really high throughput. So really what we'll see when we look at the high frequencies of 28 gigahertz on those sites, what we'll be seeing is that it'll be used for a lot of these hotspot applications where there's a defined area that needs coverage and a specific task that needs to happen. So for example, like Industry 4.0, where you're making a smart factory, or maybe an area where you want extended reality solutions, or maybe in the future when we were talking about holograms and haptic devices and stuff like that. So what we see here is that in 5G systems, it's meant to support a vast range of use cases in different industry verticals. The big challenge of 5G is to create a system that's flexible enough in its implementation to respond to all of these different use cases that have a varying nature of data. So for example, some uses of data that we have right now is like, in terms of nature of data, is maybe like email, where that data stream is bursty and it's not time sensitive, as opposed to video, which will have a much different requirement than email, which needs low jitter, which means that it needs to come at a constant rate and a constant data rate. So a decent data rate and a constant data rate to provide video. As opposed to, let's say, vehicle to infrastructure, or vehicle to vehicle, vehicle to infrastructure communications for self-driving cars, the requirements for that communication would need negligible latency and needs to be ultra highly reliable. And the other end of this is that our IoT devices, where they might be out in the field for years, sending data once a month or once a week or something like that, and have ultra low battery consumption. So when we look at all these different applications for the 5G system, it's putting different pressures on building out devices and their applications and quality of service and all of that. And so as a side note here, there's lots of opportunity within this 5G ecosystem for non-telecom companies to build out their own systems and they can enter the market for niche applications. What we're really seeing here is that these systems are going to be there not only for smartphone usage, but also for a whole bunch of industrial uses that are running in the background. At the conception of 5G, there are three major requirements to support all of these use cases. Enhanced mobile broadband, which was meant to handle speeds of 10 gigabits per second. Massive machine type communications. So what we're talking about is really large scale Internet of Things, which might need to support up to 1 million devices per square kilometer. And on the other end of the triangle, there is ultra reliable and low latency communications, which are meant to support applications with low latency like self-driving cars or mission critical applications or industry automation. And generally, that latency spec is somewhere less than 1 millisecond. When we look at the use cases from an engineering point of view, the requirements conflict with each other. You can't support everything with the same system. For example, if you want to have low power consumption devices, that conflicts with the idea of having your radio always on and scanning, which would be the case for low latency applications. For very high data rates, it's impossible to maintain if you need to support 1 million devices per square kilometer. So overall, we've got these conflicting requirements that can't be supported by just one solitary unfragmented system. So when we look at all these conflicting requirements, we have to have a pretty fragmented implementation of 5G systems. In reality, the fragmentation will be implemented using network slicing or different frequency bands. And when we start to do this and add further fragmentation into the system, it will make the 5G system more complex in how these subsystems interact with each other, making the testing regimen a little bit more complicated as we go forward. This figure here is just describing the requirements that were set out by IMT. So there's IMT 2020, which are the 5G requirements, versus the IMT Advanced, which is the 4G requirements. You can see that the 5G specifications extends all of the 4G requirements. Just to put a spotlight on a couple things, the peak data rate, we're seeing a peak data rate of 20 gigabits per second, as opposed to less than 1 gigabit per second in the 4G system. In terms of latency, we're seeing latency values of tens of milliseconds for 4G versus less than a millisecond for 5G. And also for like area traffic capacity, the 5G system can handle up to 100 times more traffic or data rate per square meter. Just to reinforce this concept a little more, the different requirements don't need to reach the maximum specification in every category. So, for example, in enhanced mobile broadband, we're not expecting low latency connections there. In machine type communication, massive machine type communications, we want a high connection density, but we're not looking for peak data rates or even spectrum efficiency. And for ultra reliable, low latency connections, we want really low latency, but we're not expecting really peak data rates or spectral efficiency coming out of that kind of system, because they're conflicting requirements and they'll need to be addressed differently in the communication standards. So as we go through this presentation, I'd like to take some time to put everything back into the context of what it means for testing cycles and test setup. Currently, we're only building out enhanced mobile broadband systems. So then all the testing that's out there right now is responding to that requirement. And as we start to build out our low latency communications or massive machine type communications, there will be a whole new test suite for each one of those, and understanding and trying to understand how they all interact together within that larger system. So at this point, we're going to start talking about some of the physical complexities of testing 5G. So it does bring some additional physical complexity in the form of higher frequencies and shorter wavelengths. And with respect to the antenna and transmission technologies, it's moving towards MIMO and beamforming, which will require something called over-the-air testing or radiated testing. In the rollout of 5G, we're working with an evolution from 4G systems. To this point in time, all of our systems have been low band, sub 3 gigahertz. They've been good for providing coverage, mobility, and have decent RF reliability. Telecom carriers with have a lot of experience deploying these kind of low-band systems, but the constraint with low-band systems is bandwidth, and bandwidth means throughput. And so then comes the 3.5 gigahertz mid-band, and these are our first true 5G frequencies. They're being rolled out currently or within the next couple months or years, depending on where you are. So in here, we're starting to see that there are slightly higher bandwidths available, and which will allow us to have higher data rates to the user. And hopefully with this rollout, 5G might start living up to the hype of 5G. And as we move into the future, we'll be using millimeter wave frequencies. These are, in 5G parlance, called FR2, or frequency range 2, which will offer really high bandwidths, meaning really high throughput and capacity. But the issue with the high frequencies is that they don't propagate well. So we'll be seeing these being used in hotspot applications, possibly to run machinery or control haptic devices or something like that. So when we look at the bandwidths available in each of the bands, low band, we're seeing bandwidths of 20 megahertz. Mid band, considering also part of the frequency range 1, has bandwidths of 100 megahertz. And I guess what we can say here is that when you're looking at data on different bandwidths, it's proportional. So, for example, if you have a data rate on your 20 megahertz band and you want to transfer that over to 100 megahertz, you can have about 5 times. You can carry that 100 megahertz band can carry about 5 times more data than that 20 megahertz band. And then on top of that, we have the FR2, which are your high frequency bands, and those will have bandwidths up to 400 megahertz in a channel. So in terms of wavelengths, I think it's useful for you in the audience, for everyone to be able to visualize what we're talking about here. So when we're talking about our LTE 700 megahertz type wavelengths, they come out to around 40 centimeters. So if you were to put your arm up and then measure from maybe the tip of your fingers to your elbow, that would be the wavelength for a 700 megahertz signal. When we look at 3.5 gigahertz or the 3500 megahertz signal, that's 8 centimeters. So to visualize that, that's kind of like if you're looking at your hand, just from a little bit smaller at the span of your hand. And when we look at 28 gigahertz, we're talking about 1 centimeter. So what's 1 centimeter? Maybe that's the width of your finger. And so these are the sizes of our wavelengths. So what do these wavelengths have to do with respect to testing? I'm not sure if anybody's heard me speak before, but I always like to characterize working with radio frequency as 1/3 science, 1/3 art, and 1/3 magic. when you start working with these higher frequencies, any of your smallest misalignments or impediments in your system have a large effect on your overall output of your test. So sometimes, you're in the lab and you're shaking around components, and then finally it starts working. You're like, yes, this is it. That's the magic part of it. So it's a little bit funnier to work with the higher frequencies. Millimeter. So in terms of this, millimeter wave engineering it's considerably different than RF engineering. Millimeter wave components act differently. At low frequencies or large wavelengths, designers, they don't need to account for the phase properties of the signal, since the wavelengths are large in comparison to the component size. But when we go up into these higher frequencies and the wavelengths are small, the idea of phase of your signal plays a tremendous role. So when we look at our test setup at millimeter wave, there are issues with alignment. There's issues with cleanliness. You need to make sure that all of your cables and connectors are clean. There's issues with link budget. So then there's a really high attenuation of your signal at these high frequencies. So it's very difficult it needs experience. Working with millimeter wave frequencies require quite a bit of experience. And so I think, especially in the telecom world, this is going to be a new thing for almost everyone. On top of adding complexity with the higher frequencies, we're also 5G. We're also adding complexity with respect to our transmission technologies. So our systems are using massive MIMO and beamforming. In MIMO and beamforming, we have a number of different sets of antenna elements working together to form beams to different users in the system. The actual implementation of the system is implemented as individual RF transmitter chains connected to individual antenna arrays. I had done a presentation, the previous presentation in June of 2021 for IEEE Spectrum, covered this idea of MIMO and beamforming pretty thoroughly. So if anybody wants to refer back to that or study that a little bit further, there's a webinar that talks about it. But when we do look at this this transmitter chain, the transmitter chains are working tightly with its own phase shifter and amplifier to steer signals in the desired direction. So if we're working with frequencies like 28 gigahertz with a wavelength of 1 centimeter, even the small electrical change in electrical length, of something as little as 1 millimeter, so maybe your cable might be 1 millimeter long or something like that, it is a massive change with respect to the phase, which really affects the direction of your beam. So when you start to picture this, you also start to see that these systems, these massive MIMO antennas with the transmitters all integrated, need to be coupled together through manufacturing and not with humans, not out in the field. Furthermore, when you look at some of these RF chains connected to individual antenna arrays, there are a lot of connections there in a very small footprint. So there isn't any access for test points in that area. So you can't measure the antenna nor the components individually anymore, because they're all part of one system. As a result, we used to be able to, in FR1, do conducted testing, which means that we would be able to connect our signal generators directly to, or base station simulators directly to our handsets and run our test like that, a conducted test, because there would be test points in the system. But in FR2, in the higher frequencies, there are no test points, and the RF transmitters and antennas are all one system. that leaves our testing to be radiated over the air. This is called OTA testing, over-the-air testing. OTA testing has now become the default testing method for massive MIMO systems and for modeling the spatial properties of the propagation channel. So really, this is the beginning of a conversation about having shielded environments to do your testing. So just to summarize here, the two things that 5G adds: higher frequencies, meaning shorter wavelengths. That means we have to deal with phase of our signal. And MIMO and beamforming, which now require over-the-air testing as opposed to conducted testing. In this section of the presentation, we're going to look more closely at the types of testing that needs to happen and the growing number of test cases that will be required. With respect to the 5G standard, all of the user equipment needs to be tested to ensure that they conform with the 5G specifications laid out by 3GPP. The first stage of conformance testing is RF conformance. RF conformance refers to measuring the transmitter and receiver characteristics at each band. So we're talking about like peak power, spurious signals, adjacent channel interference, that kind of stuff. And so it needs to be tested each band that the user equipment needs to communicate at. And so as we increase the number of bands, means we're increasing the number of tests. Then comes RRM conformance. That's radio resource management. And radio resource management looks at things like how the UE interacts with the G node B, the 5G radio. So we're talking about mobility, power control, scheduling, cell search and cell selection, handovers, and all of that needs to be tested in the RRM conformance period. And finally, there's signaling conformance, which refers to the negotiation with the overall system for connection. So like, for example, maybe a UE might need a special service, so then it needs to ask for a default dedicated bearer. And in that case, it needs to make sure that the signaling with the MME or the MME function of the 5G system adheres to the 3GPP standards. So in this slide here on the bottom right-hand corner, I've got this picture of a test setup, and I'm using the Enritsu test setup just because they're the sponsors. But there are other vendors with similar equipment, as I've mentioned, like Keysight and Rohde & Schwarz. A majority of the FR1 testing can be done on that setup to the left. So then the way that would work is that you have your user equipment, it has test points, and then you would run cables from the test equipment to your user equipment under test. As opposed to when we move to FR2, now there's a requirement for a shielded environment for radiated over-the-air testing. So then when we look at all of this testing that we've outlined here, and as soon as you start moving up into the 20s, 30s, 40, 50 gigahertz range, all of that testing needs to happen in a shielded environment. And so that's that testing system to the bottom right there in the picture. Carrier acceptance testing. So for a majority of carriers, unless you're like Dish Networks, who is building a greenfield system in the United States, 5G is an add-on to their existing system. For example, many carriers still have their 3G systems up and running, And some of those 3G systems are handling voice still, if they haven't implemented an IMS, or if they don't have 100% 4G coverage. On top of that, they might have a 4G system. And then now they're possibly adding a 5G system. So when you look at each of the carriers, they're at, and especially around the world, each carrier is at a different stage of implementation of the system. So there's a lot of complexity that is carrier specific. So a lot of carriers will ensure that any of the devices that they add to their network or allow their consumers to have really is interoperable with their network components and network implementation. Because what you don't want is to sell a device out into your network, and then it's not working right. Maybe, let's say, for a specific 5G to circuit switch fallback phone call or something like that. So you don't want that to happen, and so you need to do carrier specific carrier acceptance testing. So furthermore, carriers will want to field test the devices to ensure that the handovers are happening correctly, voice calls don't get dropped in certain scenarios, and devices not roaming when it should be on the home system, and so on. Finally, a lot of telecom carriers, no matter of the technology, have realized that the quality of experience is an end-to-end measurement and doesn't end at the device, but the application on the device. And on the other end, it doesn't end at their network element. It ends at their application server. So this adds a whole new paradigm of testing that does not only include basic conformance testing and ensuring devices work the way that they're supposed to, they're also looking deeper within their network to ensure that they have the possibly good content distribution networks. They optimize battery consumption. They implement security protocols the way that they would like, that there's seamless handovers between technologies, and all of these other variables that affect the quality of experience of their users. So we've talked about conformance testing and carrier acceptance testing. Both of those rounds of testing happen before a piece of user equipment goes out into the network, as opposed to regression testing. Regression testing happens afterwards. It has to do with software updates and continual testing of devices that are on the system. For every firmware upgrade or of the network element or device, there needs to be a set of regression tests that determine whether or not those devices or network elements are continuing to operate in the way that they're supposed to operate. So if you can imagine this idea of regression testing and what it looks like at a carrier or even a network element manufacturer, Nokia, Ericsson, Samsung, Huawei, those types of companies, there's a lot of regression testing that needs to happen. So the way that it would look is that you would have tens of radios connected to tens of or hundreds of chambers, and in between there you might want to add maybe channel emulators or RF switches in order to automate some of the testing. So then it's quite a big production within these companies to make sure that their firmwares don't affect the performance of their devices. It's also, as we look at this, it's a component of carrier testing that will become more complicated as the number of test cases increase. And furthermore, what we'll see is that the test scenarios will start to differentiate, requiring different test setups. All right. so over here, so like the idea so far is that there's a lot of testing to do. Let's start looking at some of the complexity that comes along with the 5G deployment and all of these different options that need to be tested for. So just as it gets started off with, there are standalone and non-standalone options for deploying 5G. Generally, any pre-existing carriers that had a 4G system before, and they need a way of deploying or slowly implementing 5G into their network. And the most popular way of deploying 5G into their network is option 3, NSA. So the idea is that the LTE radio would handle all of the control signaling and provide an option to connect to the 5G radio. The radio connection could use a number of different options, from dynamic spectrum sharing between 4G and 5G systems, or dual connectivity, which allows the user device to receive channels or bandwidth from both the 4G and 5G radios, as you can see in these diagrams. Option 7 and option 4, NSA, haven't been rolled out yet because the 5G core isn't in a state that's ready for major carriers to adopt just yet. So quite possibly when the 5G core is ready, we'll start seeing a mixture of option 7 and option 4 in our carrier networks, depending on each carrier's plan and how they're planning on rolling out. And then many years from now, I think the plan is to roll out to an option 2 there, which is just an end-to-end 5G core to 5G radio network. So now when you take this back into conformance testing or carrier acceptance testing, whenever you have devices deployed into your network, you can't pull them back out. So you need to ensure that those devices are okay in the network that it's going into, and be as ready as possible for the network that it will be in the future. So when you're doing your carrier acceptance testing, you got to make sure that all of these different possibilities are kind of accounted for. Just to look at the NSA option 3 a little bit closer, there's a number of sub-options within this, really looking at the data path or user plane connectivity. So there's an option where the 5G radio is connected to the LTE core directly, or through, let's do what's on the screen first. The 5G radio connects to the LTE radio back to the EPC, and that's what we see on the diagram on the screen. And the other option is that the 5G radio can be connected directly to the LTE EPC, the core, back to the core network. And so each one of those are slightly different deployment options. But what option 3 NSA is showing us is that there's an idea of dual connectivity where our UE, or our user equipment, is connected to both the 4G and 5G systems at the same time at the radio. So on the air interface now, this is a little bit more complicated with respect to device testing and assurance, because the user equipment would need to receive frames from both the 4G radio and 5G radio at the same time. However, the operators need to ensure that the equipment works with non-standalone deployments, which they already have, and is future compatible with standalone 5G deployments in the future. If we think about this setup right here, think about what needs to happen in a handover scenario where the LTE base station needs to get measurement reports and then hand over to the other LTE base station. They need to drop the carriers and add new carriers. There's a lot of interaction and complication that happens in just a simple handover. But now when you add in this situation where it's coming from multiple sites and then going to multiple sites and reassociating with multiple sites, there are issues with maybe dropped packets and latency in that connection and a lot of things like that. So all of that needs to be tested. Furthermore, when you look at dual connectivity, there's a whole bunch of different options with there. There's options where there's interband dual connectivity, which means that the frequency bands are on different bands. There's interband, so then they're same frequency band, but then the channels are non-contiguous, so that means they're spaced apart, or you have contiguous. And each one of these different options is a different test scenario. And every single frequency band B, so there's lots of different options for the secondary frequency band, there's a lot of options for those as well. So then now you have to sweep through all of those different possibilities in order to do your regular RF and RRM conformance testing. Keeping in mind that sometimes frequency band B can also be part of FR2. So then now, which environment can we test this in? So then now that's one that I'm not sure there's a right answer today, but keeping in mind too that as you introduce FR2 into this, our handsets will be working with the new transmit and receive chain and entire OTA measurement paradigm. So as you add in, as you have all of this diversity and flexibility, and as the system now matures into a millimeter wave, there's going to be quite a demand on testers to build out new infrastructure to do all of this testing. So as we saw here, there's a lot of flexibility in deployment, and which has a growing number of use cases. All right, so now we're on to our final section here. There's yet to be defined use cases. And so this is where we start talking about release 17 and the continual and what other possibilities, use cases, and functionality will be let out by the standards organizations. So what else is coming out in 5G? Maybe I'll just point out a couple. There's a bunch here, but there's a couple that are a little bit more prominent. So FR2, which we've talked about quite a bit. There's license assisted, so 5G NR unlicensed. So that allows a user to access unlicensed bands as well. And so then there's some protocols to ensure that the channel is clear and all of that, which will allow for a lot of higher bandwidth applications. Location-based services. So then right now we're all of our location-based services are implemented using GPS. And so to move away from GPS and allowing the 5G base stations to do that, it will be a short time before that will be the requirement for location-based services, and it'll get you down to pretty exact measurements. So that needs to be tested as well. Or timing-sensitive networks. One, we're looking at this idea of something called preemption. And preemption means that I want to use the channel. I need to be able to kick everybody off the channel and use the channel when I need it. And so that's really the case for those low latency, ultra reliable connections. And with all of these technologies, there's always power saving improvements that need to happen as well. So in release 17, we've got a number of new use cases. So like we'll start seeing public safety, drones, automotive, industrial IoT, extended reality, and reduced capability devices. The one that I think stands out the most to me is the public safety one, because in public safety, probably what you'll do is have the public safety component have a network slice of the overall system. So then the idea of making sure that the public safety has a guaranteed network slice and prove that it's true and that it works will be very difficult to do. And so in order for any of these carriers to start to take over some of these public safety type of roles, it's one of the applications that will require just a ton of testing. Also, when you look at this, all of these, as soon as you add a use case, those use cases need to be integrated back into the testing that had happened before. So then how does the addition of these things affect what's already happening? And so that's where that conformance and carrier acceptance testing and all of that need to happen. So overall, I mean, there's a lot of things happening and a lot of testing that is required here. So far, I'm coming to a close on our system in our presentation here. When we look at as a summary, we see that we've got higher frequencies, shorter wavelengths. Those shorter wavelengths, we need to have care with respect to how we put together our system and our test setups. That's one. Number two, with MIMO and beamforming, there's a requirement for over-the-air testing. There's no more conducted testing happening, which is a huge change in paradigm for all of the carriers. The amount of flexibility that is in the 5G system to accommodate all of the different use cases and requirements really leads to a greater number of test cases. And every time you add one thing to add into the combination, it just becomes that much more to test. And then finally, when you look at releases, 5G is a constantly evolving standard. So then that means in Q2 of next year, we're going to get a new release that requires a new set of testing. All of that test equipment that's out there being used right now needs to be upgraded and ready to go for the next set of testing. All right, and so let me I just like take this little bit here to share some thoughts about all of this. Well, one is keeping up with the standards. It'll be difficult because if you're a test taker or you're responsible for doing tests, you need to really have good relationships with your test equipment manufacturer, because that equipment needs to be updated. I'm not sure how often, every 6 months, every 3 months, to keep up with the new testing scenarios. Number two, because of the amount of testing that's happening, and the thousands of test cases that already exist, automation of testing needs to happen. And the greater levels of testing automation you can implement in your lab, the better. And so the major cost of all of this is labor and wasted time here. The next part is repeatability of tests. So now, I think that there's going to be some issues with respect to repeatability of test. This is the 1/3 magic part. When you look at OTA, I don't think that there's a calibration standard set for OTA testing just yet. And if you don't have a proper calibration standard set, then in order to repeat your test and make it repeatable, it's very, very difficult. Another part is that there's probably a little bit of lack of experience in how to deal with higher frequency components. And so even little things about like cleaning your connectors before connecting them can lead to, or bending your cables too much can possibly affect the repeatability of your tests. And lastly, lab and resource management. So when we look at what's happening at our carriers and also the manufacturers or anybody who's doing these kinds of tests, the amount of equipment and the number of people and the number of tests are all vying for the same resource or same set of resources. So in a lab, I don't know what everybody's experience is, but just finding the parts to put together sometimes is very difficult. So just even like running across the street, oh no, I need to buy this, I need to buy that, and then it takes 2 or 3 weeks to buy. All of these things are going to be quite a challenge to make sure that you've got all of your connectors and everything ready to do your testing. And then also, how does everyone fit together to use those lab and resource as efficiently and effectively as possible? So those are some of the thoughts that I have, and that brings me to the conclusion of my presentation. And if you'd like to connect, you can connect to me on LinkedIn.
All right, Kevin, thank you very much for that great presentation. Very well set up and explained. I just want to start with you can hear me, right?
Yes, I can hear you. Thank you.
All right. Just making sure I went off of mute. So a kind of generic question here, but what are some of the key challenges with OTA testing?
Okay, key challenges with OTA testing. So at the end of my presentation, I kind of hit some of those points. One of the things that we see here is that with OTA testing, we're dealing with microwave, millimeter wave frequencies, and so when we look at setting up a link, the amount of link loss in the setup is really high. So what you don't want to be measuring is things that are not your device. You want to be measuring your device. And so then when you have a lot of link loss before the device, then it makes it very challenging to actually measure your device. So that's where we start talking about that calibration standard and understanding how to do calibration for it, because I don't think it's thought out fully just yet. That's one of them. And number two, I think a lot of the test manufacturers are starting to address that in the sense that anechoic chambers can be very big. And so there's a difference between direct far field measurement versus indirect far field measurements. And in the direct one is that you have your device, you have your transmit antenna, and they're spaced out by whatever distance in the far field, and that could be a significant distance, as opposed to indirect far field measurements. Usually they've got a new product out called a compact antenna test range, which has a parabolic reflector that you reflect it and then goes to the user equipment, which lowers the size of the chambers that you need to use. And I mean, another challenge is that those are very expensive.
Okay. All right. Well, I have another question here. We have time for maybe one more. This is a simple question, so you know it's a good one. What are the main reasons that peak data rate and user experience data rates are different?
So when we look at peak data rates, so when we look at any sort of wireless technology, I think there are two answers to that. One is overhead. So like when you look at data rates versus user experience data rates, peak data rate is including that overhead in there. That's one thing, and the other part of it is that whenever you use any sort of wireless system, Spectrum is a shared resource, and so when you look at those peak data rates, it's because it's not sharing the resource, as opposed to user experience data rates. They're shared resource.
All right. I just want to push out this last slide, which is the PDH certificate code for today's webinar. We are out of time, and as I indicated earlier, this session will be archived in about 24 hours, and once the archived webinar is available, a notification email will be sent to all the registrants, and that includes everyone here today. I'd like to thank Kevin for making this such an informative hour, our sponsor, and thank you, our audience, for participating in today's session. And we hope you found today's event valuable and return for future IEEE Spectrum online webcasts, in particular when we have coming up in November, again with Kevin, to continue our 6G, Road to 6G series. So thank you very much, and hope to have you back for the next one.
Thank you.